All right, so here we go with the first objective of second semester, beginning with objective 35. Now, we're starting off the new unit, Unit F, which talks about systems of equations. This first objective is solving systems of linear equations by graphing. So I just want to do a brief introduction as to what a system of equations is. You can think of a system of equations as a set of criteria or a set of equations that have a shared solution. So think of like a bunch of equations where they all have the same solution. So what makes each of those equations true? So we're going to see a few examples. Particularly, we're going to be just talking about systems of two linear equations. So the first thing I want to talk about is the number of solutions to a system of equations. Particularly, I mean linear equations. So the first thing is the number of solutions to a system of equations. When we're talking about two linear equations, we consider three cases. The first is that we have one solution. So picture that I have a line. So a linear equation, its graph is a line. And then I introduce another linear equation. And suppose that one looks like this. These two lines, these two linear equations have one solution, and that's where each of these graphs intersect. Each of the lines intersect. So where it has one solution is when we have two lines that only intersect at one unique point. So notice that these two lines, they intersect at one unique point, exactly one. The second case to consider is that we have no solution. So I'm thinking of two lines that have no solution. So if the first case was that they have one solution and it's where they intersect, where they have no solution would mean that they don't intersect. So we would have two lines that might look like this. So these two lines never intersect. I like to think of these as like railroads, right? Railroads can't really intersect unless, and that would cause the trains to crash. So we have railroads run parallel to one another. They don't intersect. So that's a good word for us, but we're going to say that this is when two lines never meet. And so that special name for two lines that never meet, I already said it, is parallel lines. All right, our third case, so we have one solution, we have no solutions. Our third case is infinitely many solutions. And this one's kind of a weird one. So, of course, we consider our one linear equation. That's where we have this line. And if we were to draw another one where if we have one solution, it intersects once. If there's no solution, it doesn't intersect at all. If there's infinitely many solutions, that would mean that it intersects in infinitely many places. So we can say that it's the line that's right on top of there. It's the exact same line. So these two lines overlap one another. So this is when you have the exact same line. And we can test that. How many intersection points do we have? Well, there's one here, there's one here, there's one here, here, here. There's infinitely many points on the line, and it's the same line, so that means we have infinitely many solutions. All right, let's draw a few examples of each of these. The first one, no solution. So we can draw in two lines that have no solution. So remember, no solution is when we have parallel lines. So an example, unlike the one we drew above, we could say that we have two vertical lines. All vertical lines are parallel. So the set of vertical lines, they have no intersection. Unique vertical lines have no intersection, so these are parallel. I'm going to draw on these little arrows. You're going to learn this in geometry. These little arrows denote that these are going in the same direction. These are parallel. So these are parallel lines. They have no solution. infinitely many solutions, so we can draw in, say we want to draw in a line here. Well, infinitely many solutions tells us that it's the exact same line, so we're going to draw another one right on top of that. So I'm going to draw this one right on top, and we have the same line. That's infinitely many solutions. And then last but not least, when we have one solution, say we have one line here, and then we'll say we have another line, we'll say it's a horizontal line. Our one solution is where they intersect. They have exactly one intersection point. So they have exactly one intersection point. Let's practice a few. Go ahead and flip the page. All right, so next up I've got these two lines, y equals negative x plus 4 and y equals 2x minus 2. Now you might notice right away that each of these lines are in slope-intercept form. So let's take a look at this first one. We have y equals negative x plus 4. The y-intercept to this line is that constant at the end, the plus 4. So our y-intercept is 4. Our slope, that's always the number right in front of x in slope-intercept form. So the number in front of x, well, we just have a negative sign. We can assume that our slope is negative 1. As a fraction, that would be negative 1 over 1, which tells us on our graph we're going to go down 1 and right 1. So let's go ahead and plot that. So we have our y-intercept is 4, so we're going to plot the point 0, 4. We'll count up 4 on the y-axis. And then our slope is down 1, right 1, so we go down 1, right 1, down 1, right 1, down 1, right 1. We'll just continue that on. Get out your straight edge, and we'll draw the line. So it's important to use a straight edge when drawing these systems because the solution is the intersection point. So when we're graphing these, it's important to have accurate graphs so that the intersection point is accurate. All right, so let's graph the other one. Again, slope-intercept form, where our y-intercept is negative 2. That's that constant here. And then our slope is the number in front of x. We have 2. So our slope is 2. As a fraction, 2 is 2 over 1, which tells us it's positive 2 over positive 1. That tells us to go up 2 and right 1. So let's go ahead and plot that. Our y-intercept is negative 2. We're going to plot the point 0, negative 2. So we'll count down 2 on the y-axis. Our slope, we find other points from there. So we go up 2, right 1. So from here, we're going to go up 2, right 1, up 2, right 1, up 2, right 1, and so on. So let's go ahead and connect the dots. And we have a graph. Don't forget those arrowheads. These are lines still. So now we've drawn two lines on the same graph. And the solution to this system, these two equations, is the intersection point. So do these lines intersect? They do. They intersect at exactly one spot. That's this spot here. So what spot is that? Well, let's count out. It's right 2, up 2. So that ordered pair is 2, 2. So remember, the solution to a system of equations is always written as an ordered pair. So I expect to see your answers in the form of an ordered pair. All right, let's move on to another one. Here we've got 2x plus 3y equals 12 and y equals negative 2/3 x minus 1. So you might notice this first one is in standard form. In order to graph an equation in standard form, the easiest way to do that is to find the x and y intercepts. So to find the x-intercept, and let's go ahead and write this is for 2x plus 3y equals 12. To find the x-intercept, we set y equal to 0. So we're going to plug in 0 for y, so we have 2x plus 3 times 0 equals 12. And then we solve for x. So 3 times 0 is 0. So we have 2x plus 0 equals 12, which is just 2x equals 12. And then our last step, we divide both sides by 2. So we have x equals 12 divided by 2 is 6. So as an ordered pair, our x-intercept is 6, 0. Now let's find our y-intercept for this equation in standard form. So our y-intercept is where x equals 0. So we're going to set x equal to 0, solve for y. So plugging in 0 for x, we have 2 times 0 plus 3y equals 12. Well, 2 times 0 is just 0, plus 3y equals 12. Well, 0 plus 3y is just 3y. So 3y equals 12. Last step, we divide both sides by 3. And we have y equals, well, 12 divided by 3 is 4. So our y-intercept as an ordered pair is 0, 4. So we're going to plot each of these points. 6, 0. So we're going to count out to the right 6. 1, 2, 3, 4, 5, 6. It's this point here. Our y-intercept, 0, 4. So we're going to count up 4. 1, 2, 3, 4. We got 2 points, so we're going to connect the dots. All right. So we get this graph here. Let's graph the other one. Well, this one is in slope-intercept form. So we can just find the y-intercept and then use the slope to find our other points. So looking at this equation, our y-intercept is negative 1. So that's going to be down 1. We're going to plot that point. And then our slope is negative 2/3. So this tells us negative 2/3 tells us to go down 2 and right 3. So from this point, we're going to go down 2 and right 3, down 2, right 3, and so on. So we're going to get this point here. You're going to connect your dots and you're going to get your line. So we get these 2 lines here. Now take a look at the graph. What do we notice is happening? We have these 2 lines and they do not intersect. They run parallel. So if you look at each of these, they don't intersect. So that tells us we have no solution. Now, a quick thing I want to note is we know that the slope of this second line that we drew is negative 2/3. We use that to find our points. To find the slope of this line, well, to go from one point to the other, we have to go down 4 and right 6. So we go down 4 and right 6. Well, negative 4 over 6 tells us that reduces to negative 2/3. That's exactly the same slope that we had in the other equation. So one quick thing that I want to add here at the end are that these 2 lines are parallel. So parallel lines have the same slope. So you can put a star next to that, put exclamation marks. Parallel lines have the same slope. So if you were to change this equation into slope-intercept form, then you would see that they have the same slope, right? Y equals mx plus b. And from the equations, you can tell that there's not going to be any solution because they have the same slope. They're parallel lines. All right, so we're going to get a whole lot of practice on this. Again, this is Objective 35, solving systems of linear equations by graphing. We'll see you tomorrow. Have a great day.